I'm going to talk about a small part of my work that I do at Strathclyde University about heat storage in mineshafts, small-scale experiments for CFD modeling. So my work is part of the STEAM project, and in short, the STEAM project is about assessing the feasibility of heat storage in old abandoned and water-filled mine shafts. And the idea is to use a renewable energy source, such as from wind or waste burning, to heat up water in the mine shaft and extract it when necessary and integrate it into a district heating network, for example. The project has a large team and we all look at different parts, and I'm mainly based in the heat accountancy working on the fluid flow and the hydrothermal modeling. So why should we bother with computational fluid dynamics? First of all, the temperature differs over time and space in our investigations, so it's very important to learn how fast do we heat the water in our experiment. That means particularly how fast does this hot water, or is the hot water transported away from our small heat source? And what we also like to study with the CFD is how deep do we impact our mine water when heating the top of the shaft. So as an example, I put up this tea and milk comparison. So if we have a density stratification, which we'll probably learn a bit more from Elke later, we sort of have different layers, and do we stir them up? So in the mine shafts, we might have salt at the bottom that we might stir up, which we don't want. Or do we create stratification like a heated top from our little heating experiment? And what we also need is a model where we can change parameters to study them fast and replicable. So when you decide to study fluid flow in a model, you first need to define your study goals really well, and maybe you come up with a solution that avoids CFD. But if you decide to do CFD, first of all, you need to decide on, do you have laminar or turbulent flow? And once you then decided that, you will also decide on the type of model. And for that, especially for the turbulent flow, you need to pay very special attention to the wall treatment and therefore the mesh selection. And then you might want to validate your model in a smaller scale if you don't have a large scale experiment yet. So what I mean with wall treatment is that, for example, which you can see here in the sketch below, is that near the wall, the viscous forces dominate. So we have different flow patterns close to the wall, and the models all treat that differently. So when I talk about the walls, I sort of talk about the boundaries of the model, which you can see here on the right in this example model. For example, you have a water and air boundary at the surface here, or you might have just a water and wall boundary with some sort of encasing material that will be attached to the side. So these are the things that you need to carefully consider. So for our large-scale shaft model, we want to couple turbulent flow in a standard K-epsilon model, Reynolds average, Navier-Stokes, and couple that with heat transfer, so conduction in the surrounding rock, but also the water, and convection in the water of the shaft. So I talked about this model last year, so if you're interested in that more detail, you can look up the last year's talk. But this year we want to focus on the small scale. So this is just a small overview. We have a 2D axisymmetric model to save on mesh sizes. So this one has a rotation axis here. So basically this is a slice of our shaft that can be then represented in 3D. And here we need to note that we heat our shaft with a closed loop pipe. So the heat source itself is quite small and only in the first 50 meters here. And we need to make several assumptions to implement that heat source. For example, a constant heat transfer coefficient of 200 watts per square meter Kelvin. And now if we want to scale down, first of all, I considered the size of the heat source and our tank to sort of match the dimensions. And we want to have a ratio of the heater radius and the cylinder that is fairly similar to create a flow that we can use to validate our large-scale model. And I used this aquarium heater with a low wattage and a water tank that sort of has or was sold as a good with a good insulation. And what we also want is a similar heat input in our small scale model. So we calculate the power that we have over the first volume here at the top. So for our small scale experiments, that's fairly easy. So we have the 50-watt heat source and some volume. And for the shaft, this is not as easy because we aren't 100% certain how much heat we will put in with this sort of closed loop pipe. So we can make some assumptions, and the most likely one is from the temperature loss of the pipe. So maybe we will be between 200 and 10 watts per cubic meter. So they are a bit different, which isn't ideal, and we see why later. So the setup of the model, of the experiment is the heat source in the middle and a few temperature sensors surrounding that, also at the wall and in the room. So if you're lucky, your health and safety approves that, which is more tricky than you might think for such a simple experiment. And let's look at the results of this small test. So here's the 2-day run on the x-axis and the temperature on the y-axis. And for example, the room temperature, which you can see here in black, showed that it unfortunately varied quite a lot in the lab. And what we can also see is that our tank isn't actually as insulating as we hoped for, because the wall temperature here, which is close to this temperature probe in the water, is almost the same. So hardly any insulation there on the walls. Also, interestingly, we can see that this temperature sensor, which sits just below the heat source, almost shows no impact from the heat source, which is interesting because it means the thermocline is really close to our heater. Also notable in here is the horizontal temperature distribution, which is sort of here in pairs, meaning that, for example, 2 and 7, they appear really close to each other. So the temperature doesn't change much in the horizontal, except for the sensor number 1, which we kind of leave out because it's really close to the heat source. So what we can see here with these bars is that we are sort of in a range 19.5 Celsius till 21.5, something to keep in mind now for the models. So for the small scale model, we're gonna set that up similarly to the large scale one, and we need to make a few assumptions again on the walls or the boundaries here in this model. And what we can see is that these different model types all overestimate the temperature despite adjusting our boundary settings. And they also differ quite a lot, which is not good. So we need to go back and look what we actually simplify there at the water-air boundary, for example. So what we assumed was a constant heat transfer coefficient at the surface, so here at our tank. But in reality, if you run a different model where you model the air, you can actually see the heat transfer coefficient isn't very constant. It follows this curve here, which like falls down away from the heat source and then rises up again at the walls. So luckily, this is fairly constant in time, so we can use one of these as a sort of function instead of a constant value. But what was also a big problem in the small scale is the evaporative heat loss. That wasn't a problem, or wasn't considered a problem in the large scale, because there the shaft is sealed. But in the small scale, in the lab is quite dry, so there is a huge evaporative heat loss, which we then add on top of our function. And now we have a closer look again at our wall treatment, because in the large scale, we use a K-epsilon model, which means our walls are just using wall functions, meaning that they use semi-empirical approximations for the actual flow at the wall. So we have a large mesh cell at the wall, whereas other models, such as the low Reynolds K-epsilon, for example, in COMSOL, they resolve these sublayers of flow individually, meaning you need a finer mesh. So When we put all these adjustments into our model, then we can see that the low Reynolds one performed quite well in the final results. So we can see that our measurements match our model fairly well. There's still a larger impact from the outside air, but that's okay for now. So what we can conclude from that is you need to be very careful when scaling down, because the turbulence or your flow might not actually scale as well despite meeting the same dimensions or same power input, because you might have different flow conditions, which you can check, for example, with the Grashof-O'Reilly number. And you need to pay very close attention to the boundary conditions in the small scale, because something that didn't matter as much in the large scale might be impacting the smaller scale a lot more with your higher surface area to volume ratio, for example, such as I've seen with the evaporative heat loss. And in the end, you need to go back to your study goal and decide which model is actually feasible, because the low Reynolds model I can't use for my large scale because there were too many cells. It would take too much computational effort to run that. So I am stuck with the K epsilon, meaning I need a large scale model, a large scale run to confirm and validate if our study goals can be met with the designed model that we have so far. And yeah, if you'd like to discuss that further, you can contact me, and thanks for your attention.